participant. So the topic that as you can see is advances in application of biomedical wearable sensor. So we'll discuss about this, and when we talk about this, particularly this evolution of this wearable devices. So we can say like today with the increase in like elderly population, the medical industry has kind of changed drastically and dramatically also, with the focus on development of biosensor that you can say enable real-time health monitoring and prevention, and then you can think of how you can be personalize the medicine, or let's say this biomedical devices that we're talking about for variety of application, and then we can talk about different disease particular to chronic and acute diseases. So this when we talk about this point of care technology, so this provide rapid and patient centric diagnostic, especially for those with limited access to health devices. So with conventional disease, let's say diagnostic tests and commonly used in particular in laboratories and hospital are kind of time consuming and costly, and that require highly trained professional, or let's say personal or physicians that are there. Whereas when we talk about particular to healthcare regime, the shift that is going on towards personalized medicine that we're talking about, and particularly globally wearable, sensor, this wearable sensor that have kind of emerged, or you can say there is a as you can see in this image also, a kind of it is emerging or exponential growth is you can see if we look into the compound annual rate also. There has been a increase from let's say 2017 to 2025. It is kind of approximated that a kind of a 40% around, or about 38% about development growth can be expected. And this wearable biosensor have received tremendous attention over the past decade, and mainly kind of concentrate in the healthcare industry, which attempts to apply physical signals such as let's say heart rate, as you can see in the image, and how it is kind of connected. Heart, you can think of blood pressure, skin temperature, respiratory rate, then body motion to to kind of extract clinical relevance kind of information. As you can see, a point of this care or all these devices, how it is communicating to, let's say if we're talking about a mobile device, and that can be connected. So when we're talking about this wearable devices, you can see in all cases the subject is wearing such kind of device, which either in the form of wristwatch, or let's say glasses, or or some kind of other way of wearable cloth, let's say, or portable devices. So those devices basically somewhere have a option or facility to communicate with the mobile, and then those data can be accessed and further can be analyzed, and so on. So, so that is what this wearable biosensor. You can refer, particularly in the biosensor field. Also, there are several growth. Whereas this biological sensor you can think of where somewhere in the watches or clothes, the bandages, let's say the glasses, contact lenses, rings, which being kind of attached to the human body and provide function that kind of distinguish themselves from existing devices in terms of portability or ease of use, and somewhere the environmental adaptability also. So these wearable devices uh, will be having such kind of this feature in it. And these wearable devices have gradually been developed in the form of accessories, which we'll be looking into what sort of what different type of that are coming up. And if we talk about the past few decades, the tremendous advances can be seen in the field of electronic, then this biocompatible material, if we talk about the nanomaterial, that has led to the development of this implantable devices and enabled diagnosis. And somewhere this small sensor or this biomedical devices that are kind of greatly, improving the, you can say, the quality and efficacy of the healthcare. So despite kind of the motion artifact, that normally if those people who are working in the field of biomedical signal processing and other sort of thing, they will be talking about whenever we think of wearing such devices, there are possibility that this motion artifact problem that might cause. And one of the major problem that are associated with this sort of wearable devices or sensor, whenever those data or the signal is being we try to extract and we try to process it, then at that time we normally see this kind of motion artifact. And those also nowadays, that is where we need to think about the sensor, the material of it that we're talking about, and how you can reduce the motion artifact in it. And then we'll try to see, let's say, we'll a example you can take like wireless wearable ECG sensor. We'll come to the different type of wearable sensor also. But when we talk about this wearable ECG sensor, you can see these images that being formed here. These are this uh, you can say, whenever any electrode that come in contact with the body or skin, they try to form a electrical circuitry, and this is kind of equivalent circuit we normally talk about, which will be formed. As you can see at this side, you have this body part where we have dermis, then epidermis, then here there is the contact with the your let's say the sensor or the electrode. So that will be again will be as you can see, gel is there, so gel will be placed, and then this electrode will be placed on the let's say on your arm or forehead, wherever you intended to pick up the electrical voltages, and that might be in the form of millivolt or microvolt. And to reduce that moving artifact, whatever we're talking about, this electrolyte gel normally being used, and this sort of electrical circuitry, or it will form. So the signal will be picked up by this sensor. The sensor, there are different shape and size of the sensor. If we talk about ECG sensor as well, that depends again where you are putting those sensor in your forearm, or in either in the their chest, in the chest also you can put the sensor. So that will that is a different domain where in the size of the sensor or the wearable sensor that can be placed. And we'll discuss on that also. This is a kind of a capacitively coupled electrocardiography, and this is kind of mostly most common kind of electrography, or normally we say CCECG, and that being used, kind of a non-contact ECG, and that require long-term kind of convenience if we talk about the user sensor interface. And we let's say in patient ICU or somewhere being placed, and being those kind of sensor being then he or she need to on, and the signal can be picked up and can be monitored for a longer duration. So this is and again this is the circuitry that we talk about, how it can allow like the here you can see this, the different sensor will be placed at different part of the body, and then what sort of then it will be placed basically in the body skin if we try to form the this kind of electrode placement and the representation of the CCE system. So then basically we have the instrumentation amplifier, this low, or you can say, strength signal that to be amplified. And then we have we need to take care of this, artifact also, moving artifact, or let's say other sort of noises. So we normally try to form a band pass filter by using low pass and high pass filter. Then noise filter, basically to remove 50 or 60 hertz of power line interference that normally is there from AC supply if it is being connected. So these are, you can relate with the pre-processing also, and then obviously the signal that to be converted into digital form, and then whatever kind of application, if that is mean for some wireless transmission, you can do that also here. So you can see this is, let's say this is your input signal, and then this is being kind of processed, and this one is a kind of filter. You can see the power line interference is present in this signal, and then somewhat it is being corrected over here with after this band pass filter is being applied using low pass and high pass. Still some noise is there, so that is also clear after this. So this is how it can be processed. And once you have the like let's say filter signal, then further analysis is kind of can be done by the physician. Because if you give like as an engineer, if the device is not properly functioning, and the physician will only look into the signal. So even if with the noisy signal, they will won't be able to recognize the different wave like PQRS and T wave, and they cannot able to differentiate whether it is a normal signal or it is a kind of a signal with some kind of cardiac problem. So it is our kind of as an engineer, it is for us to to do the kind of calibration, or let's say to maintain the system and to see whether it is properly picking up the signal and displaying the signal or not. So this is again whenever there is a kind of a integration is there between a system and let's say human body. So in between that, that is what we are talking about, with what sort of sensor that can, those sort of signal can be picked up. And picking up those signal, as we are talking about signal with millivolt range, as you can see, this signal are with millivolt range. Even some, if we talk about EEG brain signal, so that will be in microvolt range. So those signal, and picking up those signal is the sensor that to be used, which sort of electrode is kind of compatible to pick up. Like if we talk about ECG, AGCL normally being preferred. So that also you can think of. So now let's move to portable devices, which we are talking about, or let's say this different kind of this wearable sensor that we're talking about. So here you can see from early, if we talk about the 21st century, these wearable devices have begun to provide a kind of personalized health services, as well as advanced level of personalized portable devices and sensor. And currently, the portable devices can be classified as wrist, watches, bracelet, gloves, as you can see in the image, heads. The heads, where you can think of glasses, helmets, and when it comes to the body clothes, it can be coats, underwear, or let's say pants, and then feet, or the and the body sensor control devices also you can think of, where shoes and other sort of thing where the sensor can be mounted or integrated, and that can be worn, and that will give you the different parameter. So due to the the you can think of the nano scale level or micro scale level, or let's say, minimizing the size of this biosensing devices. The development of this microelectronic or wireless communication technology, and this wearable monitoring system deeply embedded in our kind of life that we have kind of further, develop. And this wearable sensor physiological measurement of interest in, you can think of rehabilitation, where it can include, let's say, heart rate, respiratory rate, because as you can see, different part of the body can be targeted, and there are different ways to, mount this sensor into those wearable, item or that we normally use. And then we can think of blood pressure, blood oxygen saturation. Then if you want to have sort of muscle activity related, thing, so those sort of, sensor can be also can be mounted. Then parameter extracted from such a measurement can provide indicator of health status and have tremendous diagnostic value. Until recently, kind of continuous monitoring of this physiological parameter was possible only in the hospital setting. But today, with the development in the field of this wearable, technology, the possibility of accurate and, you can think of continuous, then real-time monitoring of physiological signal is kind of, it is there, it is possible, and in reality that is happening. And integrating this physiological monitoring in a, let's say, wearable system, sometimes require kind of a different, let's say, novel sensor location, or let's say the design aspect also you need to think of. And if we think of, let's say, if you see the fingertip, there is a ring present here, and if let's say this ring sort of, sensor that being used, that for what purpose that can be used, that for measuring the blood oxygen saturation, SpO2, and again heart rate. Whereas in this COVID scenario also, there has been certain, advancement you might have seen in, because this SpO2 and heart rate was one of the major factor that, normal people, they always they were tracking all this parameter during this phase. And there has been different, devices that are available. Wristwatch is again there, but still this ring type finger ring type also devices can be there. And it integrated technique for kind of motion artifact reduction, whereas, and designed to improve measurement sort of accuracy. And when we talk about the application of this ring sensor technology, or let's say the range of it, then particularly for diagnosis of this hypertension, to the management of cognitive heart failure, in that way also it can be used. And because somebody is wearing a ring, let's say he or she is not willing to wear any watch and is fond of wearing a ring. So in a ring, let's say, the, physician, they ask a, a manufacturer to have sort of a ring which normally he or she likes to wear. So they have the
Hello.
sensor in it. And yes, yes. Should I continue, or there is, I think, some noise?
Sir, sorry, sir, I muted the participant.
Okay, no problem. So this this is what, and again, if we look into other sort of like, as you can see, different like headset, and then we have watch, then we have shoe. So different sort of, let's say, body parameter that can be targeted, and from those, the signal, or let's say the data can be extracted, and that can be further processed. And there has been again, biochemical sensor are also there, which is also gaining kind of and great interest among the among the researcher in the field of wearable tech.
Sir, sorry for the interruption. Like 1 second, you give me, sir. I'll mute all the participants, and you can please unmute and talk again.
Now it is fine, I guess. So that good.
Yes, sir. Please, sir.
Okay. So again, this advances in the field of let's say this wearable biochemical sensor have has been there, and but it is not that fast as the other technology. If we
Sir, you're muted.
Sir, you're muted, sir.
okay. Hope now it is fine.
Yeah, perfect, sir.
Okay, so that what I was talking about, the advances that are going on in the wearable, biochemical sensor, and that is particularly slow, but still that is going on at the micro and nano level towards fabrication technologies, and that will also pick up at a certain time where different sort of application that are there. There is a need to address those. So again, when we're talking about this, the growing interest in the field, let's say in the development of self contained lab on a cheap kind of a system, and such a system can be kind of something which has a potential to grow, and it will serve particular kind of point of care medical, let's say testing and diagnosis that are that being done by making testing and diagnosis fast and cheap, and somewhere kind of it has to be easily accessible. So this development of system on chip, that is SoC, which kind of sometimes integrate this a pH or let's say temperature sensor for remote kind of monitoring application also. So that those are also there. So let's try to see one by one when we talk about this. When we talk about wrist mounted devices, so as you can see the different application of it, or where particularly how we'll be using, like non-invasively kind of monitor blood pressure, and which can include optical pressure, and then it is possible for towards ECG kind of sensor as well. So for let's say for physiological monitoring that have developed commercially with a kind of improvement or involvement of this battery longevity, and the minimization of this hardware for converting the raw signal into real-time interpretable data. So this wrist mounted devices such as let's say fitness band or smart watches are kind of moving from basic accelerometer based smart and this speedometer to include biometric sensing, and typical non-invasive monitoring devices. It can be kind of, as you can see, it can be categorized into communication with electronic devices, then monitoring of human physiological signal and human activity signal. So in that way, it can be mainly it can be categorized. As already we have discussed, blood pressure, that is possible for individual health status monitoring, and then ECG also is there. So this is what like you can relate with the wrist mounted devices or the sensor that are being used for wrist mounted. And then head mounted devices also, as you can see, there are different sort of um, applications that are now coming, and there has been a recent advancement in this field also. Even there are this VR technologies that are coming off. You can see different gaming console also, and somewhere you can relate that, towards medical field also. You can take and you can have different sort of kind of application where smart glasses can be worn, and it is again smart glasses can be head mounted devices, and which can help us for pulse sensing, kind of like PPG that we know, photoplethysmography sensor can be mounted, and that can be put in those mounted devices, and you can able to get PPG signal also. And moreover, then this smart glasses can also be fabricated with sensors such as accelerometer, gyroscope, then barometer, then magnetometers, and GPS. And the more advanced smart glasses are called Recon-Jet, and they kind of aim to capture information about, let's say somebody is wearing those, and that particular subject. While let's say riding a bicycle or running, or let's say just in a quiet position also. So all sort of information can be acquired, and it can be analyzed like the daily routine of that particular person, how their physiological parameter is changing, and that is what. And the e-textile, if we relate to, if we jump to e-textile zone, where there are like you can say this electrochemical sensor kind of application, where those are powerful analytical tool, which you can think possesses of or like kind of rapid detection of biomarker in clinical specimens. And while most electrochemical sensors are fabricated on rigid substances, so there is a growing need for sensor that can be manufactured on inexpensive and flexible material. So as you can see in the images also, so the sensing, these are the sensing area, as you can see. So if this is a design, it can be look like a design, but basically the sensor are mounted on it, and that are mean to have the let's say some sort of like electrochemical kind of sensor, which will get information from your body. And for this wearable sensing application, this sensor could be integrated with miniature sensing electronics on textile using let's say conductive ink or thread, or can be data could be or transmitted wirelessly to a peripheral devices. For example, smartphone, if it is there nearby, it can be connected, and you can transmit the data. Further, the advancement in the electronic textile may also enable electronic to be directly integrated into garment, thereby improving the device portability, and somewhere we need to take care of user comfort as well. So keeping all into mind, the e-textile can be in the textile, it can be done. And needed integrated sensor also. Here it is, we're talking about the EEG. In the right hand side, you can see the EEG data that can be acquired, and that can be processed, or further it can be sent, or wirelessly you can send to another place, and that can again you can process. So this is in this they have talked about a health monitoring system, namely they have named it as Wealthy, and the system is based on textile wearable interference implemented by integrating sensor electronics and connecting in fabric form. Advanced signal processing technique has been used, whereas modern telecommunication system also is being integrated. The sensor, electrode, and the connection are realized with conductive and piezoelectric kind of settings, and this sensor that is being knitted in a fabric is produced in a one-step process, and the procedure of that is to kind of this that so feasibility of a system based on a fabric sensing element. And this is what you can that this particular system can be used let's say for ECG, particularly at different place. When we talk, basically people might be knowing the sensor can be put on different limb and chest. Or instead of putting in the limbs, the nearby position has been picked up, and those places those electrode has been placed, and then further it is being processed with this portable patient unit, that is the PPU. That is kind of a local processing, you can say communication unit or network, and through that the EEG signal are sampled with let's say with a set of 250 hertz, and then it is processed. And what sort of in
Tirupati Laddamma, Tirupati Laddu.
Again, I think there is some noise. So you can think for extracting information sort of heart rate, or let's say you are aiming towards finding out somebody is having arrhythmia, so you can target QRS complex also. So on that, those sort of meaningful number or of sample can be extracted and can be processed. Or let's say you are talking about ischemia, so you can target T wave or ST segment also. Again, patient monitoring in the home and community settings. Here also there is certain growth if we talk about this wearable technology, and that has gained interest also. If we talk particularly in European country, they are more concerned about the elderly people. And as you can see, I'm associated with ISTI Italy, so they're also they are getting fund towards sensory kind of application, where how you can make life more comfort for elderly people. And the kind of we talk about, that is ambient assisted living on this sort of connected devices, so that they will not face any sort of problem of, if any, it can be properly informed to nearby, or possible, let's say, to a hospital or caregiver or clinician or family member, those who are away from that particular place. So this is what you can see here also different body parameter ECG. Let's say somebody is not able to walk with a railing or with a grip, or with some support, they're walking, or the motion has been tracked. Then he or she can be given a e-textile data glove if he or she can want that. And with that also sort of information can be extracted. And this is kind of a system where connected way the data can be extracted, and it can be assessed at any point. Like it can be, as I mentioned, at any sort of point you can extract heart rate, respiration rate, or all sort of thing. And it can be this is so as to give proper attention and to address the patient at before any sort of emergency. So if the data is changing, or let's say the daily routine, if there is some sort of information that you, after assessing the data, you feel that there is a need to look into it, so you can address the subject before it goes to a more serious situation. So that is what. And this is also the same sort of thing. You can relate with the rehabilitation also, and all sort of information can be extracted. And As again, you can talk about here Internet of Thing also, the application of IoT and this physiological data or movement related data from the patient, that can be continuously somebody can monitor, and real time way data can be extracted and can be analyzed and further can be communicated to nearby places, and if any need that to be addressed, it can be addressed easily. Again, e-textile, a system for remote and continuous monitoring. Earlier we are not talking about remote or continuous monitoring, so that is also possible, like wearable system for patient remote monitoring, mainly that consists of sensing part and the data collection hardware that to collect this physiological and movement data. Then there has to be one kind of communication hardware that you can see, and software that to relay the data to remote center or other place, and then data analysis technique to extract the relevant clinical information from this physiological and movement data. And then you need to you can have a continuous way of monitoring also. And somebody, let's say, have sort of problem, so he or she, without going to a hospital, he or she can own sort of thing, and the information can be extracted and can be analyzed for a duration, and then if there is a need, then the problem can be addressed. So this recent advances in the sensor technology and this microelectronic telecommunication and the data analysis technique have enabled this kind of development, and you can say deployment system for patient remote monitoring. So that is there. And again, you can relate with the this microelectronic system MEMS technology here also, which is like again booming area, and you can talk about the system on chip implementation also in this field. This is one of our work recently that we have published in 2020, I guess, and where this is again wearable textile antenna. We try to develop antenna and which can be worn in a let's say in a shirt or pant, and the data can be what any like physiological data can be extracted that can be sent from this using this antenna. So that is one example as you can take off. Then there is again this monitoring individual during exercise. There is a need also, and people those are aware of obesity and other sort of problem. They have this kind of let's say interest of wearing this wearable technology, so as to wellness or fitness kind of you can relate with the monitoring and the potential development. This sort of industry, this is booming, and again here also you can able to extract information like respiratory rate, heart rate, ECG related information, then SpO2, then oxygen saturation also, and continuous monitoring can be done, and a daily routine can be maintained in this way. So in this also, this is also again another wearable technology that we're talking about. This is the headset that we have already discussed, but if we take it into a gaming console using wearable and wireless EEG based BCI, this BCI is brand this board this the integration of this the computer and this the brain. So here basically you can have this sort of sensor, as you can see here, this EEG module, and you can have this sort of sensor, dry sensor that are used, and there is a reference channel. There are different sort of EEG sensor like 16 or 32 or 64 channel sensor also, or with capping type it can be also used, and for this brain computer interface. And but here, let's say the idea is to there is a integrated system and you are playing a game. Let's say you are aiming a target, and basically with your brain signal you are trying to control the aiming target. So in the computer, basically you have a set target, and you have to meet the target. If you are pointing to the center of the target, so at that time you can say the focus level is high, and if your focus level is not high, you might deviate from the target. So basically with your brain signal you are trying to control, and you are playing this game. So this is BCI kind, this brain computer interface kind of a integrated gaming console. But really interesting because that might, you can take this application towards other sort of, let's say, robotic arm. Let's say if somebody try to design a robotic arm, he or she is not has lost a arm, so to meet the requirement, you need to have a robotic arm, and that robotic arm need to be controlled via this EEG signal. So how you can do it with this sort of application? The signal can from the brain can trigger the robotic arm and can function the arm, because ultimately, let's say you want to move your arm, so from your brain the signal is being driven, and your limb is or your arm is functioning, or it is moving. So this is where this algorithm has been beautifully they have given in their papers, where the target, as you can see, user is targeting, and how you are they are comparing with a baseline focus feature they have, and then based on this the level of this focus, the focus level, the target that hitting the target, you can able to reach to the near to the center of the target. And if your focus level is low, with lower focus level, you might deviate from the target. And that is what this focus level and non-focus level wise they have divided the level, and you can apply this sort of BCI kind of gaming console also. Again, there is another paper which we have published recently. This is a very you can say this brain imaginary based EEG signal classification, or let's say in a simple way, if we try to say, simply you are just imagining something in your brain, and and uh, and here, as you can see, a hand movement and a foot movement, and you basically you are not actually doing that movement, physical movement you are not doing, and but what you are doing is you are just imagining in your brain that you are moving your hand or you are moving your foot, and in that process you need to train it while recording the data or while collecting the data, and then some feature need to be extracted from the signal, and after extracting the feature, that can be classified with as you can see, there are different classifier we have used. So how you'll be extracting the signal here, there is the use of this sensor, like the EEG sensor that being used. Those sensor will be placed on the on your head, and the signal will be extracted, and the you only thing that you have to take care is when you are extracting the signal with after training or the environment also, you need to take care of all set of thing you can look into while extracting the signal. We have basically set up a environment where we have given training, and after sort of training, then we have extracted the signal, and a classification also we are able to get a class with this, that it is you can easily classify with hand and foot movement. And this with BCI dataset, also sort of dataset that are already existing BCI competition dataset. With that also we have tried, we have extracted with we have done it with real-time subject also, but that we have not included because that still some work is going on, and we need to get the approval, ethical clearance approval with those subjects. Then only we can go for publication with those data set. But similar data set, the data sets are available. So once you have your concept ready and the model ready, you can apply with the other set of similar data set, because it should be reproducible and you can able to get the result. And this is another paper, I guess, and or the same set of paper where you can see here the brain from where different part of the brain in the signal has been extracted. This different electrode has been used, and because we're targeting the motion related information, so few electrode might play vital role, because you know brain have different areas where that mean for different activities. So we targeted those area where the motion related activity that take place, and we have done that classification. So these are a few of that result when we have done it. So the process of that, and so this you can see classification result and other thing after extracting. And this is again another work. It is 2014 or 15 we have published. This is on EEG. So again, EEG we have used with standard data set, but again with in lab we have used EEG machine that we have with and then this NI-LVIS as kind of it helps us to take those signals in a real-time manner to the system, and in MATLAB we have analyzed it. Semi-real-time manner you can think of. We have tested or cross-validated the result that we have achieved with the standard data set. So we have basically the idea is to do the classification among let's say arrhythmia, ischemia, and the healthy sort of group. So in the result also you can see the three different class: arrhythmia, ischemia, and healthy. So here also you can see the result, like this is one, let's say this is one group, this is one group, and this is one group. So in the clustering also you can see different quick cluster. So in that way, this signal where we're talking about this wearable sensor. So this signal, EEG signal, is being captured with the electrode that being used for ECG recording, and then the signal has been then processed, and you can take it for such kind of application, like classification of abnormal, let's say, and normal um, subject. Then again, we have here is wearable kind of ECG monitoring also. This earlier with the rehabilitation also there also we have discussed, but again here you can think of this IoT that I was talking about, and the advancement of this. Again, you can think of this 5G technology that are coming up. So there is a possible way of kind of a wearable patch ECG monitor that can run on a cloud computing platform, and the ECG data is kind of transmitted locally from free living subject wearing those sort of sensor through a gateway to that can be via your micro Bluetooth to wireless link, or other sort of thing to cloud, and you can access the data at any point of time, and you can analyze it. The storing, analyzing of at different location, kind of referring to another physician, those sort of thing also can think of, because let's say at your locality you do not find a cardiologist and you want that data to be referred to another place. So uh, this sort of integration with the wearable ECG monitoring is possible, where a kind of the data can be analyzed at different place and can be sufficient like information can be extracted so that the patient can be addressed with each of convenience. So this is the this is like remote monitoring with 5G. This body area network also that is where the 5G that are coming up and providing that is high bandwidth for two ways of communication between healthcare professional to let's say central server. So for patient to a personal trusted kind of gateway that is called as this PTZ. And if we consider possible scenario that can show why.
Excuse me, sir, you're
Sir, you are
muted.
muted, sir. Akash, sir, you are muted.
Okay.
Yeah.
Okay. So I was talking about this, remote monitoring with 5G and this personal gateway, trusted gateway, how you can able to protect the data from, let's say, because we've been talking about in the medical field also how the data can be protected or you you can share with the trusted, partners, and it can be referred uh, with let's say with the physician, and it can if there that you do not want to share all the health related information, or let's say any kind of personal information that are related to the subject. So this sort of gateway will help, and this wireless sensor can be used, and this body area network, when we are talking about that where you can relate with the this wearable devices, and that network can be formed, and with that when you are connecting with the this gateway, the data can be shared among the other partner where with this obviously with the 5G, because as you are talking about the bandwidth and high bandwidth and two-way communication is also there. So this is what, and again, here again, when we talk about this gateway, it is kind of a more powerful device that can handle both authentication and authorization that I was talking about. And again, there are like three possible situation when access to device of this body area network may require different approaches for this authorization, like let's say emergency kind of condition, somewhere non-emergency SS by patient trusted gateway by, let's say, a dedicated personalized entity, then non-emergency SS by patient trusted gateway by authorized entity, and that is based on the context, let's say location, presence of specific devices, and sort of thing can be done. So this is somewhere. So in this way, it can be done, and um, this whole on this wearable devices you can relate to this also. So this is what I planned of covering today. I was a bit fast, I think, in my thing, and I have covered before the time. So thank you for listening. Please do let me know if anyone having any sort of query.
Okay, so thank you so much for the wonderful session, sir. So now it's time for the participants. So if you have any queries, anything to ask, sir, you can please ask him now.
Sir, very interesting
Thank you for.
and informative also.
Thank you, sir.
Any queries, any questions to ask, sir?
Ma'am, open the mic.
If anyone is not able to, yeah, please raise your hands using the smiley stay. I can unmute you.
Yes, ma'am. This is a very nice session and very deep knowledge. I got the very deep knowledge about the all the technologies and sensing devices. Very nice.
Thank you.
Okay, so in case of no queries, we can wind up the session here. And the once the 10 days FTP is over, I'll share the recorded session with all the participants. Thank you so much, sir. Like that was really so in depth, and you have given us a lot of knowledge on so much topics. And that sensor things was like all good. And it was really kind of you to show your results, and that was so motivating and inspiring too. Thank you so much, sir.
Thank you. Thank you. Thank you.